My dear students, let me welcome you all to a new edition of physics. In this edition, we'll learn about AC circuits. In each circuit we'll try to determine whether the voltage and current are in phase. Also, we'll try to get an expression to obtain the phase angle between voltage and current. And there is something very important we want to obtain. It's an expression, for example, that determines the opposition that the current faces in the circuit. So let's get started. AC circuits. We'll resume talking about AC circuits. Okay, in the previous edition, we talked about the circuit that contains pure inductance, and now AC current and voltage in a capacitor. Okay, so in front of you we've got a circuit that contains AC source and a capacitor. As a matter of fact, the charge on the plates of the capacitor is determined from the relation Q is equal to C times V. C is the capacitance of the capacitor, and V is the potential difference. Okay. Potential difference applied across it. It is generated by the dynamo. So instantaneous voltage, denoted by V, equals V maximum sine omega t. And the current is given from, yes, Q over T, or dQ by dt, since I is given by dQ over by dt. So I, substituting for Q, it is d by dt CV maximum sine omega t. Okay, so I equals C omega V maximum cosine omega t. Once again, cosine is replaced by sine. Okay, so it is omega t plus pi over 2. Once again, I is equal to C omega V maximum sine between two brackets omega t plus pi over 2. So I is equal to I maximum sine omega t plus pi over 2. And of course, I maximum is equal to the product of C omega V maximum. The two equations, equation number 1 and 2, okay, we'll obtain something. It is quite clear that the current leads the voltage by 90. Okay, from the relation I maximum is equal to C omega V maximum, we can determine the capacitive or capacitive reactance as follows. I maximum is equal to C omega V maximum. So V maximum over I maximum equals XC, and it is equal to 1 over C omega, and omega equals 2 pi f. So XC equals 1 over 2 pi f C. And it is shown in front of you the relation between capacitive reactance and frequency. It is an inverse relation. Okay. Connection of capacitors. It is the opposite of resistors. First of all, series connections. When we have two or more capacitors connected in series. Okay, so the circuit shown in front of you contains 3 capacitors. Reactance of the first, XC1, of the second, XC2, and XC3. And we want to obtain the total reactance. How to obtain it? Since V equals V1 plus V2 plus V3, so we can say Q over C equals Q over C1 plus Q over C2 plus Q over C3. So 1 over C equals 1 over C1 plus 1 over C2 plus 1 over C3. So C total equals C over N if they've got the same value. Okay? And what about if they are connected in parallel? Talking about parallel connection. It is shown in front of you. We've got 3 capacitors connected in parallel to the supply, and we want to obtain the equivalent reactance. Okay, Q is equal to Q1 plus Q2 plus Q3. So VC is equal to the product of VC1 plus VC2 plus VC3. So C is equal to C1 plus C2 plus C3, and it is equal to NC if they've got the same value. Okay, when the capacitors have the same capacity. And now talking about another circuit, L and R in series in an AC circuit. So we've got an AC circuit powered by a dynamo, and it contains ohmic resistor and pure inductance. It is shown in front of you, okay, a circuit that contains, yes, pure inductance L and resistor R connected in series to AC supply. Voltage across the inductor is denoted by VL, and that across the resistor is denoted by VR. Okay. VR are in phase with the current, but VL leads by 90. Leads by 90 on the current. Thus, the 2 voltages can be drawn to a scale shown in front of you right now. VR and current are in phase, but VL, yes, leads by 90. And what about the total voltage? Okay, this is the total voltage. And now we can obtain it. How? Total voltage will be, yes, square root VL squared plus VR squared, applying Pythagoras theorem. Okay, we can say V is equal to square root VL squared equals I squared XL squared, because VL is equal to the product of I and XL. And VR is equal to the product of I and R. So VR squared equals I squared R squared. And of course, I squared will be taken as common factor, and out of the square root will be I. So V equals I square root XL squared plus R squared. So V divided by I will give, the quantity that represents opposition. We call it impedance, denoted by Z. So Z equals V over I, and it is equal, of course, square root XL squared plus R squared. Once again, Z is the impedance of the circuit. From the figure, the voltage leads on the current by an angle theta. Previous figure shows that the voltage leads by an angle theta. If we want to determine the value of theta, tan theta equals VL over VR. Tan opposite over adjacent, VL over VR. Okay, so tan theta equals IXL over IR. I will be crossed out, so tan theta equals XL over R. And theta, yes, is given 10 to the power of negative 1 between 2 brackets XL over R. Important hints here. We've got something important to bear in your mind. Definition of impedance. It is defined as the quantity that determines the current flowing in a circuit that contains reactance and resistance. Okay? It is the combined effect. It is the combined effect of reactance and the ohmic resistance on the passage of the alternating current. Let me say it again. It is the combined effect of reactance and ohmic resistance on the passage of the alternating current. And now we've got another circuit, C and R in series in an AC circuit. C, yes, indicates that we've got a capacitor. R, ohmic resistor, non-inductive ohmic resistor. They are connected to a power supply, AC power supply. It is shown in front of you. And once again, voltage across the capacitor is denoted by VC, and it is equal to IXC. Voltage across the resistor, VR, and it is equal to IR. Okay. Voltage and current are in phase in the resistor. Okay. But voltage lags by 90 on the current when talking about the capacitor. So VR are in phase with the current, but VC lags by 90 on the current. Thus, the two voltages can be drawn to a scale. V is equal to square root VC squared plus VR squared. So V is equal to I square root I squared XC squared plus I squared R squared. We can say V is equal to I square root XC squared plus R squared. In this way, we can determine the impedance, which is equal to V over I, and it is equal to square root XC squared plus R squared. And as I said, Z is the impedance of the circuit. From the figure, the voltage lags, yes, the current by an angle theta. We want to determine the amount of this angle. Tan theta equals VC over VR. So tan theta equals IXC over IR. VC is equal to the product of IXC. And VR is the product of I and R. So current will be cancelled out. So tan theta equals XC over R. And theta itself equals tan negative 1 between two brackets XC over R. And what about the circuit that contains capacitor and inductor, pure capacitor and pure inductor in series to an AC supply? Okay, it is shown in front of you right now. Voltage across the coil is denoted by VL, and it is equal to IXL. Voltage across the capacitor, yes, it is denoted by VC, it is IXC. Okay. And vector diagram, yes, the vector that represents the current, the vector which represents the current is shown in front of you. I, VL leads by 90, VC lags by 90. Okay, so it will be VL minus VC, but this happens when VL is greater than VC. So V equals VL minus VC when VL is greater than VC, or VC minus VL when VC is greater than VL. Okay. And also talking about the reactances, XL, when XL is greater than XC, total reactance, yes, X is given by XL minus XC. Or total reactance will be XC minus XL, and this happens when XC is greater than XL. And finally, what if the circuit contains RLC? So RLC series circuit. R indicates or refers to ohmic resistor, L inductor, C capacitor. They are all connected in series to an AC supply. Once again, voltage across the inductor is denoted by VL, and that across the capacitor is denoted by VC, and that across the ohmic resistor is denoted by VR. VL, product of IXL. VC, product of IXC. VR, product of IR. If VL is greater than VC, vector diagram is shown in front of you. VR is in phase with the current. VL leads by 90. VC lags by 90. So when VL is greater, direction of VC will be changed, but we have to put a negative sign. So the vector that represents the difference between the two voltages, VL and VC, is shown in front of you. Okay. And if we want to represent it by reactance, also shown in front of you. And now, V is equal to VR squared plus V minus VC all squared. So we can say V is equal to, VR squared is equal to I squared R squared. VL squared is I squared XL squared. So I squared will be taken as common factors between two brackets XL minus XC all squared. So V equals I between, so V is equal to I square root R squared plus between two brackets XL minus XC all squared. In this way, we'll be able to obtain, yes, the impedance denoted by Z. So Z is equal to V over I. It is equal to square root R squared plus between two brackets XL minus XC all squared. In this case, the total voltage, in this case, what case? When VL is greater than VC, the total voltage leads on the current by an angle theta. We want to determine the value of theta. Okay, tan theta equals VL minus VC over VR. So tan theta is equal to IXL minus IXC over IR. I will be crossed out, so it is equal to XL minus XC over R. And theta itself equals tan negative 1 XL minus XC over R. And what if VC is greater than VL? Okay. VC is greater than VL, so we'll change the direction of VL and put a negative sign. Okay, this is the vector diagram for voltage, and vector diagram for reactance is shown in front of you. We'll do the same exactly. Voltage is equal to VR squared plus, and now we'll start with VC minus VL all squared. So V is equal to I squared R squared plus I squared between two brackets XC minus XL squared. I is taken as common factor. Okay. Square root R squared plus XC minus XL all squared. So impedance equals V over I, and it is equal to square root R squared plus between two brackets XC minus XL all squared. In this case, total voltage lags on the current by an angle theta. To determine the value of theta, tan theta, yes, is calculated. It is VC minus VL over R. It is equal to VC minus VL over VR. So tan theta equals IXC minus IXL over IR. So tan theta equals XC minus XL over R, and theta equals tan negative 1 between two brackets XC minus XL over R. And now talking about something very important, it is resonance state. What about this state? Since the inductance causes the current to lag behind the voltage, and the capacitance causes the current to lead the voltage, therefore, they can be adjusted to cancel the effect of each other. At resonance, the current is at its peak value, its maximum value, and the impedance is at its minimum value. Impedance is then equal to the ohmic resistance. It is then equal to just the ohmic resistance. So once again, at resonance, what happens? VL is equal to VC, because XL is equal to XC. Okay, total voltage will be equal to the voltage across the resistor. Total impedance is equal to the ohmic resistance. Voltage and current are in phase, and this means phase angle is equal to 0. Okay, this happens when we obtain resonance state. At resonance, XL is equal to XC, so VL is equal to VC. Total voltage is equal to the voltage across the resistor, and impedance is just equal to the ohmic resistance. Voltage and current are in phase. So at resonance, XL is equal to XC, so we can say 2 pi FL is equal to 1 over 2 pi FC. So 1 equals the product of 2 pi FL times 2 pi FC. So 1 is equal to 4 pi squared F squared LC. So F squared equals 1 over pi. F squared is equal to 1 over 4 pi squared LC. In this case, we can obtain resonant frequency. It is 1 over, square root of 1 over 4 pi squared LC. So resonant frequency, it is 1 over, 2 pi between two brackets, or square root LC. And we can say, of course, F1 over F2 is equal to square root L2 over L1, C2 over C1. Impedance of RLC series circuit. When the frequency of the applied voltage changes, the impedance of the RLC series circuit changes. XL is equal to 2 pi FL. Since XL is equal to 2 pi FL, so the relation between XL and frequency is direct. So XL is directly proportional to the frequency and directly proportional to the inductance. So the inductive reactance is represented by a straight line that passes through the origin. If we want to plot the relation between, reactance and frequency. But talking about capacitive reactance, it is equal to 1 over 2 pi FC. So XC is proportional to 1 over F. We've got an inverse relation. So the capacitive reactance is represented by a curve that approaches the two axes. And what about the ohmic resistance? Yes, thank you very much. Ohmic resistance, if you remember, it is given from, R is equal to rho E L over A. So it is independent of frequency. So it is represented by a straight line parallel to the frequency axis. If we plot the relation between opposition and frequency for each item, we'll obtain a straight line when talking about inductive reactance. And it is a curve when talking about XC, capacitive reactance. And it is a horizontal line when talking about the resistance. And to combine all of this, it is shown, in front of you. Relation between impedance and frequency. And we've got something very important. It is resonant frequency at which XL is equal to XC. And now we've got important hints. The relation between current in RLC series circuit and frequency will be represented with the the graph which is completely the opposite of the previous. So this is the graph that shows the relation between current and frequency. There is something very important. Resonant frequency is the frequency at which XL is equal to XC. And impedance, of course, yes, is minimum and is equal to just the ohmic resistor. So factors affecting resonant frequency are inductance of the coil, capacity of the capacitor. And this way we've come to the end of this edition. Until we meet again, my best wishes to you all. Thank you very much.